Hello. For the first of these assignments, you will be required to calculate ensemble averages and partition functions by doing an explicit enumeration over all the accessible microstates for a system of n particles. In this video, I am thus going to discuss an algorithm we can use to generate all the accessible microstates. Before I get onto the algorithm, however, let's first check that we can generate all these microstates by hand. So for this exercise, we're going to consider particles that can have one of two possible states, up or down. This single particle system can be in the two microstates that I've just showed there. It can be in the state up state or the state down state. Now consider a system of two of these particles. Pause the video and try to work out all the states that a system containing two of these particles can be in. Hopefully, you managed to work out that there are four possible states for this two-particle system. There is the state shown here in which both particles are up. There is the state in which the first particle is down and the second is up. There is a state in which both particles are in this down state. And last but not least, there is the state where the first particle is up and the second particle is down. Doing this by hand is all well and good, but ultimately what we are going to need is an algorithm for generating all of these different microstates with a computer. To get started on that, I have redrawn these four possible states at the bottom of the slide. I have also assigned each of these four states a number from 0 to 3, as you can see here. The numerical label that I have given to each state probably seems arbitrary. I have a rule for going from the state to these labels, however, which I would like to explain now. So the first part of this rule is that I say that all spins in the up state are given a value of 0. Okay? States in the down state, meanwhile, are given a value of 1. I can thus express the coordinates of the particles in the state 0 as 0, 0, the coordinates of the particle in state 1 as 0, 1, the coordinates of the particles in state 2 as 1, 0, and the coordinates of the particles in state 3 as 1, 1, as shown here. Now notice that if I multiply the first of these two coordinates by 2 and the second coordinate by 1 and sum the resulting two numbers, I recover the numerical labels at the bottom of the slide. So for state 0, I have 0 times 2 plus 0 times 1 equals 1. For state 1, I have 0 times 2 plus 1 times 1 equals 1. For state 2, I have 2 times 1 plus 0 times 1 equals 2. And for state 3, I have 2 times 1 plus 1 times 1 equals 3. Great. Here is the result from the last slide once more. Let's see if we can extend this idea to a system of three particles. First, pause the video and see if you can write out all the microstates that a system with three particles can adopt. Hopefully, you wrote out these 8 states shown here. I'm now going to label these states with single numbers, like this. Furthermore, it's easy for me to write out the three coordinates of the particles using the same rule as before. 0 is up and 1 is down. Now, what three numbers do I need to multiply these digits by to recover the individual numbers at the bottom of the slide? The answer is 4, 2, and 1, which you can confirm for yourself by pausing the video at this point and working through all the maths. Notice that 4, 2, and 1 are all powers of 2. 1 is 2 to the 0, 2 is 2 to the 1, and 4 is 2 squared. This recognition is important as it allows us to see what we are doing here. The coordinates that we have written for our microstates in the first row of the table are the binary representations of the numbers that we have written in the bottom part of the table. This is the basis of our way of generating all the microstates. If there are n possible particles which each have 2 possible states, there are 2 to the n possible states. Each of these 2 to the n possible states can be mapped onto one of the numbers between 0 and 2 to the n minus 1, as it will be the representation of that number in binary. We can thus write a loop that converts each of the numbers between 0 and 2 to the n minus 1 to the binary. These 2 to the n binary representations are the 2 to the n microstates we need. More generally, if there are n particles that can each have m possible microstates, then we can map them onto the numbers between 0 and m to the n minus 1. To generate all the microstates, we write a loop that converts each of the numbers between 0 and m to the n minus 1 to its base m representation. These m to the n base n representations of the numbers are our m to the n possible microstates. The idea that we have covered in the last slide is important, so let's cover it again by introducing this piece of code that generates all the microstates for a system of 5 particles that can each be in 2 states, state 0 and state 1. We are looking at a system of n spins here, and each of these spins can be in 2 possible states. So there are 2 to the 5 possible microstates, and 2 to the n microstates to enumerate. The loop generates all of these states because we run through it 2 to the 5 times. Inside the loop, to generate each microstate, we call a function called convert to binary that takes the number of particles and the loop index as input. This function will return the microstate by converting the number that is passed to it to its representation in binary. This is relatively simple, but there is still one issue that we need to address. How do we convert numbers to binary? Alternatively, how can we convert the number 28 to its binary representation? Well, first note that 28 is less than 31, which is the largest number that we can represent with 5, the number of particles, digits of binary. We next note that we can write 28 as shown here, where the A0, A1, A2, A3 and A4 are the ones and zeros that are going to make up our string of binary digits. Let's now divide our input number 28 by 2 to the 4 and take the floor of the results. If we do the same set of operations on both sides of the equation above, we find the following. Now, 2 to the 0 over 2 to the 4 is less than 1. Similarly, 2 to the 1 over 2 to the 4 is less than 1, as is 2 squared over 2 to the 4 and 2 cubed over 2 to the 4. In addition, the A0, A1, A2 and A3, that these quotients are all multiplied, are all binary digits that are either 0 or 1. These first 4 terms in this expression are all going to be less than 1. We can thus disregard them when we take the floor of the quotient. The only number that can be greater than or equal to 1 is the final term, which has a to the 4 multiplied by 2 to the 4 over 2 to the 4. The 2 to the 4 over 2 to the 4 is 1, and the floor can thus only be 0 or 1, as it must be equal to A4, and A4 is 0 or 1. Now, if we complete this calculation with 28, what we find is that A4 is equal to 1. Let's now suppose that we subtract A4 times 2 to the 4 from 28. As shown here, we then get the following sum with 4 terms on the left-hand side of the expression. All we have done here is subtracted the A4 times 2 to the 4 from both sides of the original expression. We have just learned that A4 is 1 in the previous step, however. We can thus proceed as we just did, by dividing 12, i.e. 28, subtract 16, by 2 cubed, and taking the floor of the result as shown here. By this logic that I've just explained, this gives us the value of A3, which, when we do this calculation with 12, is equal to 1. To convert a number from base 10 to binary, we thus proceed as was by alternating the two steps that I've just described. To complete this whole procedure, we thus start by dividing by 28 by 2 to the 4 and taking the floor. This gives us 1 for the first digit of the binary string. We then subtract the 16 that this 1, as the first digit of the binary string, represents from 28 to give us 12. The second digit of the binary is then extracted by taking 12 and dividing by 2 to the 3 to get, and taking the floor to get 1. We then subtract what this 1 in binary represents, which is 8, from the 12 to give 4. The floor of the 4 is then divided by 2 squared, and we take the floor once again. This gives us another 1, and then we subtract what that represents from our number to get 0. It is then straightforward to show that the final 2 digits of binary are 0, which we get by doing 0 divided by 2 to the 1, and 0 again, which we get by dividing 0 by 2 to the 0. We can use these ideas to write the Python function convert to binary, which is shown here. Notice that at the start of this function, we create a numpy array with n elements that will hold the n coordinates of the particles in the microstate. It is this array that is returned at the end of the function. The output from this function will thus be a numpy array that contains a series of 1s and 0s. Inside the loop, we do the 2 steps that I've described in the diagram. The step in which the ith element of the numpy array state is set is the one of dividing by the various powers of 2 and taking the floor, that is here. The next line then does this step that removes the part of the number that are accounted for by earlier binary digits. Notice last of all that if your particles have more than 2 states, it is easy to modify this function. You just need to change the 2 here to m, where m is however many states each of your particles can be in. Hopefully that should be enough to get you started on generating all the possible microstates for a set of n particles that can each be in one of m different states. Try the exercises to see that you can apply what was covered in this video. Good luck, and thank you for your attention.